Hello and welcome to Algorithm Integrity Matters. Insights for financial services leaders who want to enhance fairness and accuracy in their use of data, algorithms, and AI. I'm your host, Yusuf Mullah. So this is the second in the series on explainability. So this article was titled Algorithmic System Integrity, Explainability, Part 2, Complexity. The too long didn't read. Complexity must be actively managed rather than passively accepted. Data relevance directly impacts both accuracy and explainability. Technical visibility techniques can be useful. So in the last episode, we explored the concept of explainability, its importance, and 4 challenges. In this one, we explore some solutions to the first challenge, complex algorithms. So just to recap that challenge, complex models can operate as black boxes. Their internal processes are so complex that even their developers may struggle to explain how inputs lead to specific outputs. This poses several problems, and we've listed 3. So the first of those is trust. Customers and other stakeholders are wary of automated decisions that they can't understand. Second is compliance. Regulatory frameworks and standards are now calling for explainability, especially for decisions with significant human impact. And then errors. When we can't see how a model works, it's harder to spot and fix mistakes. So on to solutions then. Banks and insurers can use several methods to address this problem. Here are 3 sets of commonly used methods, each of which work better when cross-functional teams are involved. So the first of the 3 solutions is simplification. So we want to strike a balance between accuracy and simplicity. Simpler models can be easier to explain, but may not be as accurate as the more complex models. There's a diagram in the article, which you can see if you click through the link to the article. And that basically depicts performance or accuracy versus explainability. That article is reproduced from Zhang et al., and it's titled Model Explainability versus Model Performance Comparison. So in general, the more complex models that often produce more accurate results are harder to explain. Simplification can include establishing clear thresholds, so determine what an acceptable trade-off between complexity and explainability is, and use this to choose the model that suits. Implementing validation. More complex isn't always more accurate, so don't miss the opportunity to use a model that is easier to explain and equally or more accurate. And then developing parallel models. In some situations, you may want to create simpler, interpretable models that approximate the complex ones. If you can get them close enough, you may be able to use them to explain. Okay, so that's the first solution, or potential solution, being simplification. The second is data selection. If the data going into the model is not relevant, it can make it difficult to determine how decisions are reached. There are situations where irrelevant data can result in more accurate predictions. But if the data is not relevant, then this accuracy gain might be a technical improvement, not a real one. We also need to be careful not to eliminate relevant data. And this can vary depending on the use case and the nature of the system. For both internal data and external data, carefully choose the relevant data and use data only for its intended purposes. There's also a discussion about eliminating protected attributes, and we'll explore that in a future article because it is quite a long story. So that's the second solution, data selection. The third are visibility techniques. These methods work best when combined with proactive complexity management from the previous sections. There are several techniques that we can use to interpret model processing. And this list, of course, as is the list of solutions, is not exhaustive. What to use will depend on the use case. So there are 4 listed. The first is scenario testing. We conduct what-if analyses to demonstrate how changing inputs affect outcomes. SHAP, so Shapley additive explanations. These calculate feature importance scores. And this method is used to explain the output of machine learning models by assigning each feature a value for a particular prediction. Then we have LIME, so these are local interpretable model agnostic explanations. We just call it LIME. These create linear explanations of complex decisions, and this method is used to explain individual predictions by approximating the model locally with an interpretable model. And then finally, we have PDP, so partial dependence plots, and ICE, which are individual conditional expectation plots. These create population level and instance specific feature impacts. These methods are used to visualize how features affect predictions on average, that's PDP, and for specific instances, that's ICE. Now, with all of this said, in determining which methods to use, we need to consider regulatory requirements. So, for example, GDPR's right to explanation, and also operational constraints, that is, the computational resources that are required. And in our next article, next episode, we'll focus on the second challenge, being complicated processes. That's the end of this article. Thanks for listening.